Our next speaker is Dr. Amit Kumar Dutta. He will be talking about terahertz communication, actually a little bit or more on the waveform design for terahertz communication. Dr. Amit Kumar Dutta is working as an assistant professor at IIT Kharagpur. Prior to this, he has a lot of industry experience at Texas Instruments, Broadcom, and NXP for almost 14 years. He has several IEEE transaction papers and US patents to his credit. He did his PhD from IISc Bangalore. His current interests are in general physical layer, 6G, and quantum signal processing. The floor is yours, Dr. Amit Kumar. One request is, can you please try to limit to 15 minutes or so, so that we can stick to schedule. Thank you.
Yeah, am I audible?
Yes.
Okay. Just let me know if I can
share the screen. Yes, please.
Has it come?
Yes, we can see the screen.
Okay. Good morning. I think thank you all. Professor Abhinav Kumar has done a small summary at the terahertz communication level. So I'll go little about one of the aspects of the waveform designs for the wideband terahertz communication that we are currently working on. So these are the contents: why terahertz, few applications, what are the different channel model and its approximations, and one of the candidate for the terahertz communication, and naturally its MIMO extension, and what are the different standard perspectives and study items that we are planning to submit at the THz level. In fact, this talk, a part of this talk was in the submitted 4 months back at THz workshop for 6G perspective and all. So it is more on the extension. So obviously, why terahertz? It's basically start from the 100 gigahertz and so on and so forth. Huge available bandwidth, meaning it's not even auctioned. So you have a bandwidth of like 20 gigahertz, 50 gigahertz kind of things, provided your hardware can support it, obviously, but it's an unlimited bandwidth that you can have it. And the only thing, as you can see, as you have heard from Professor Ravinav's talk also, that it can be a short range communication. But people now are thinking of making it a V2V or vehicular to vehicle, even within a short range. And that's how the perspectives and that's how the possibilities of the terahertz comes into picture. This is few of the applications which not limited to, but broadly they are present. One is the broadband communication, where our interest is indoor and V2B communication, and then you have imaging and biomedicals, industrial applications, and so on and so forth. A list is long, so I have not put all of them. This is the typical indoor communications for a terahertz communication systems, where each and every beam can be of a TBBS kind of data links. So that's why the terahertz interest come into picture here. But what are the problems? We talk of terahertz, the problems is the following. So if you look at the complete spectrum of the terahertz, I have taken it from one of the paper there. It starts from 60 gigahertz, starting a little bit on the millimeters website, to 1 terahertz. You see a lot of bumps here, right? You see the path loss, and there are a lot of bumps. As you progress towards 300, 500, 600 gigahertz, the bumps actually start increasing. In fact, around 1 terahertz, the bumps are so wide, and the gaps are also very small. So this is one of the nature of the terahertz thing. So obviously you can avoid the bumps, but bigger question that arises is that if you take a 20 gigahertz bandwidth within the band, how do you ensure that the channel gains and all things are exactly constant? That is something not possible, because it's a wide band effect, right? And that's what drives a lot of researchers to model approximately what could be a wide range terahertz channel model. And there are a lot of works on that. I'm not getting into that, but I'm just explaining what approximate model has been proposed, and which basically kind of drives us to propose a different type of waveforms. So obviously, few of the challenges not unknown to anybody. It's kind of coming from the UWB concept, where people have seen these issues, but now it will be much more prominent, because we are not talking of 20, 30, 50 gigahertz kind of bandwidth. Okay, and this effect, the frequency dependent effect of the channel is severe in terahertz, because within the band, you cannot ensure that all your channel gains remain constant, which essentially means that one path cannot be just an all-pass filter. It is kind of a band-pass filter. And that's typically the wideband effect. So what are the solutions that we have? I'm not getting into too much details into it. So the solutions that people have proposed, so this is just a kind of a simplified channel model where it is just a simple indoor communications. And when you say that this is more of a, it's saying that the paths do not have the constant gains and all. So let me just get into the diagram here. So what does it mean? Does it mean that if within the band, my gains don't remain constant, can I think of slicing the band as the bread is there? I hope I'm not increasing your appetite. So can I think of it's like a big band, wide band, and can I slice it and use those small slice as my baseband unit and do processing as a whole? So that drives us the channel model, that drives us the waveforms. So this is the typical terahertz waveforms, not waveform, that are terahertz channel models that has already been proposed. I have not mentioned the reference here. So it's basically a parallel FIR filter. If you can approximate a narrow band as an FIR filter with some sort of a finite length, so you can have some parallel number of FIR filter depending on what is the slice of that bread you are taking. If you say 100 megahertz, 200 megahertz, 250 megahertz, one subband, like that, you can have say 20, 30 such slices, and you have each and every band will have its own characteristic. So this motivates typical waveform. So this is what the terahertz channel model that has been approximated to, and that's drives us to have a interesting waveforms. So this is one of the waveforms that a part of it was proposed earlier, but now we have made it kind of FFT as well as filter bank based. This is one of the work from our side. And it's a generalized model. So that's the beauty of it. So you have a bunch of FFT, like normal IFFT, and then you have upsampler, and then you have band shifter. And like that, for each and every band, it will be treated like a normal narrowband system. Okay, and you have, if you slice your band, say m number of small narrowband, you can have as many number as that many number of IFFTs, chains with respect to the number of bands here. And then finally, you can have beamforming after that. And that's where the terahertz part coming into picture. But there is a problem with this. I mean, we cannot avoid it, but this is how uninteresting proposals that we came up with. So you can see that a part of this architecture, which is a pure baseband, a part of it will be working on a low speed baseband. And another part will be working on a high speed baseband. So if you say I have a 20 gigahertz, bandwidth, so I'm essentially talking about 0.05 nanosecond. I don't know if any hardware has that, digital hardware has that 0.05 nanosecond kind of clock speed. So this is one of the architectural issues which has to be addressed in next decade or whatever. But this is what the architectural aspects. So now if you can think of this architecture, each individual parallel one is actually addressing one-on-one slicing. Okay, this is one of the terahertz beamforming part, though it is a simulated one based on that architecture. It's not a real one. I mean, we don't have the terahertz actual antenna, but it is more of a simulated one where we have taken a huge array and saw how much beam width and how much narrow beams that we can create it. And naturally, this is the RX part of it, which is just the opposite part, where you have the combiner, antenna array, and just the reverse process of what the TX is. You have a bunch of filters, then downsampler, and then FFT, and then that's it. Now, this addresses some of the CFO issues, some of the other interference issues very well, because you have a front-end filters. But as mentioned earlier, how to design this front-end filter, can it be part of the standard? I'll explain it. And that's how the standard comes into picture here. Okay, this is some of the spectrum that we simulated. So it's just like some 5-band systems. It's the TX and RX. Left side is the TX system, and RX is right side is what we received, the proposed architectural part. Now, next comes to the MIMO. Now, this is more of an open items because if you have a multi-band systems, most of the hybrid beamformings are with a single band system. Now, there are works on wideband systems as well. get it there. But if I put together the filter banks and Waveform together, the existing hybrid architecture, hybrid beamforming will not work. It will have a lot of phase shifts and a lot of issues there. So we had to use one of the blocks in between, where we call it subband combiners. Okay, so apart from your standard precoders, you have to have another optimized filter, or you can say it's a matrix that's called subband combiner. That that's kind of nullify the effect of all your front-end filters, and that has to be there, and that becomes our design challenge for your optimizations. Naturally, that is the RX side, where if you had a subband combiner, you have to have a subband separator at the RX side as well. And this works pretty well. At least we had done a simulations and it really working well. So this is one of the test bed setup that we have used it, where we are using our own 5G release 16 compliant test bed file layer that we have developed at the IIT Kharagpur in-house completely. And this whole system, we are planning to put it on the RF SOC ZCU1. But unfortunately, the THz channel part, we cannot get a real system because we don't have the hardware, right? So 200 or 300 gigahertz RF with phased array antenna at the TX level, we don't have it. And I don't know whether it is commercially available or not. If anybody knows, we are ready to procure. But this is what the current setup, where we'll be just sending IQ samples, put it in a computer, and MATLAB will get the real data. And then again, it will put it to the real FPGA. This is how the complete setup that we are planning to test it on the 5G platform. So this is a 5G platform. Over and on top of that, we are putting the 6G waveform based, terahertz waveforms. That part. This is a simple simulations, and it worked well. This is only for the non-MIMO system, like a single antenna systems, but it's a UPA, 200 gigahertz, 5 gigahertz bandwidth, and we have taken a small subband of 250 megahertz, and that works pretty well with whatever proposal that we had. Now, coming back to the standard. So what is the takeaway from the standard perspective, and what exactly the study items that we are proposing, and we are working on that? What about the slicing of the terahertz band? So how do we slice it? What should be the slice width of the subband? Will it be 50 megahertz? Will it be 100 megahertz, 200 megahertz? Can it be adaptable? That's exactly one of the research items that needs to be addressed. Okay, so this is how to determine this minimum subband size. And we believe that it has to be dynamic based on the environment, based on, other things. For example, if it is a rainy season, the terahertz bands, the absorption will be even more. So in that case, you have to decrease your subband size. So now you are talking of that kind of systems where your system will be now environment dependent. So now this is one of the challenges from the standard point of view. As I just said, it depends on the environment very much because of this absorption part. Okay, so this slicing, whether it's uniform, non-uniform, has to be part of the standards. Then subcarrier spacing and the length of each IFFT. Now, usually terahertz, we are talking of slightly static system, but when you talk of the V2B kind of environment, obviously there will be mobility. So how do you adjust the subcarrier spacing? Should I increase it? If it is, then how much? And what should be my IFFT length or FFT length? Those kind of, obviously as part of the standard, that has to be mentioned. So, and it has to be thoroughly evaluated. CP length, naturally, because that determines how you can have your filter designs and other parts there. Synchronizations of the sequence, because we have done synchronizations for the 5G respective. But when you have multi-band system, how exactly a synchronization should be there? Because it is a multi-band system, right? So should it be just a one-band synchronization or multi-band synchronizations? Again, that needs to be found out at the standards.
Amit, can you try to please wrap up in a minute?
Yes,
because
sure.
We were supposed to start the panel at 11:30.
Yes, we have. I understand. So next, the zero padding between the two subband, because we have a lot of filters. So obviously there has to be some zero padding, and that should be part of standards. And it also depends on the quality of service that an application demands. And what about the filters that we have talked about? All this LPF, BPF, should it be part of the standard? And pilot structure, because we have seen that subband to subband, there is a high frequency correlation. So obviously you can exploit it, and there should be some pilot structure adapted to that. Okay, so I would like to acknowledge for this work This project is actually sponsored by SHART, Government of India, under the Channel Estimation and Waveform Design in Terahertz Communication for 6G. And then I would like to acknowledge MathWorks, because we are completely doing it in-house 5G testbed development using Simulink to FPGA. No RTL, no VHDL, nothing. Everything is automated for us. So it really reduces time, and there is a great help from them. TSDSI for encouraging this work, and IIT Kharagpur for giving me the infrastructure. Thank you.
Thank you, Dr. Amit. I mean, it's actually very interesting that there are lots of fundamental research problems in terahertz. I think we should all form a group and drive this in TSDSI quite soon. We should start looking at this item in TSDSI very seriously. I mean, given that people are talking seriously about this in 6G. Thank you again.